Okay, so let's start. Uh, so my name is Patrick Monroe. I'm a research officer at Gerard. And so thank you for coming here to this workshop about CPLEX and Python. So I think before we start, it's important if you want to follow along that you go download the material, the workshop material on the GitHub page that I created yesterday. So if you don't, you probably have received an email. You've probably received an email concerning this related to this GitHub repository. But if not, you can go to the Gerard website. So if you go just gerard.ca and you go to Activité événement and you click on Atelier CPLEX or CPLEX Workshop if it's in English, you can find the link to the GitHub repository. You can find on the GitHub repository some information about what to install. So hopefully you all have Python 3.12 or maybe an older version would also work, but not a newest one. So if you have, for example, Python 3.13 or 3.14, you most likely won't be able to install CPLEX or do CPLEX because the latest version of CPLEX is not compatible with the newest versions of the newer versions of Python right now. So that's why I ask you to install 3.12. If you have another version, it may work, but I'm not 100% sure. So maybe some of the functionalities won't work. I don't know. I tested it with 3.12. I use also Visual Studio Code, but you can use something else if you have your favorite IDE, you can probably use it. And also there I mentioned how to create a virtual environment and how to install CPLEX with the pip package manager. It's very easy as we're going to do it together, as you'll see. And if you have an academic license, you don't need it actually for this workshop, but it's free if you're a student or if you work in academia. So you have to download to register online and to download the official CPLEX version. And when you install, after installing with pip CPLEX and do CPLEX, there's a little another line that you have to call here. I'll do it with you, but it's just to upgrade to tell CPLEX and do CPLEX that you're using the academic version and not the free community edition of CPLEX. But as I already mentioned, so for this workshop, the CPLEX Community Edition should be enough. The only difference is the number. There is a restriction on the number of variables and constraints. So if you most likely if you have like a real instances and you work on real life problems, it won't be enough. But for the kind of problems that we'll be solving in this workshop, it's certainly enough. So are there questions before we start? No? Okay. So let me first create the virtual environment. So this is what I did here. I just cloned the repository, so the Gerard CPLEX workshop repository. So you see on the left here the data slides and the source code. So you can, in VS Code, you can open a terminal window, and then we can create the virtual environment. So in Windows, to use, I have on my computer also Python 3.14, the newest version. So I have to specify the version of Python that I want to use. If you're on Mac OS and or Linux, I think you cannot really, this command would not work, py and 3.12. I wrote here what you have to do. Usually it's called directly like Python 3.12, and you can do that. And then we call minus -m and vn, and again the name of the virtual environment. Here it could be the dot. Here it could be .vnv if you wanted to make it hidden folder, but it doesn't really matter. You can give it the name that you like. So now it's creating the virtual environment. It takes some time. And once it's created, so we have to activate it with this command. Or in Linux or Mac OS, you have to type source before creating the virtual environment. By the way, for the virtual environment is not really mandatory. It's recommended whenever you start a new project in Python, because so that you don't have conflicts with other libraries that are already installed, other packages. But it would most likely work if you, even if you don't create a specific virtual environment and you use the global environment of your system. Okay, so now we've activated the virtual environment, and we can install CPLEX and do CPLEX. So in there, you don't really have to type Python -m. It will most likely work. It's just a pip install and the name of the packages. So CPLEX, do CPLEX. In order to run all the code that we'll be using in this workshop, we'll have to install also some other packages like matplotlib, networkx, but we can install them later. Let's just start with the CPLEX and do CPLEX. And so now the community edition of CPLEX and do CPLEX have been installed. And I will show you, if you have the academic version, how you upgrade your do CPLEX to this academic version. Actually, it's just typing this line here. So do CPLEX config upgrade. CPLEX config upgrade, and you type within parentheses the path to the CPLEX, the CPLEX software that you installed, where you installed the academic version. So here it's probably something like in Windows, program files, IBM, iLog, CPLEX Studio, something like that. I'm not sure what it would be like on Mac OS or Linux, but probably something similar. And then it does some stuff. It found the DLL. There is no error message, so it most likely worked. Okay, great. So now let's start with the content of the workshop. So okay. So first, what is CPLEX? So if you're here, you've probably heard of CPLEX, about CPLEX before, but maybe you've never used it. Maybe you've used different mathematical optimization solvers. But CPLEX is used to be is still one of the most famous CPLEX solver. I think maybe today Groby might be a bit more used on CPLEX, or there are other optimization solvers that are maybe more used today than it used to be. But CPLEX used to be the most used one at some point. And so what it's used to do is it's used to solve optimization models, which include linear programming, mixed integer programming like MIP or MILP, also some quadratic programming, piecewise linear problems. And probably those are just some examples. That includes also other capabilities that I didn't mention here. And it uses, in general, exact methods to solve those problems. So the simplex, for example, to solve LPs or barrier, and a branch and bound, branch and cut to solve mixed integer linear programs. And what's interesting with CPLEX is that you have an API, so some kind of interface with different languages. And so we have here Python, Java, C, C++, .NET. And one of them is one of those languages that is very popular nowadays is Python. And in this workshop, we'll look at this interface between Python and CPLEX. So how to call CPLEX through Python. So those are the topics that will be covered, or at least a subset of them. I'm not sure if we'll have time to cover all of them. But we'll start with the do CPLEX. So I will explain you a bit in a few minutes what's the difference between do CPLEX and CPLEX, because as you saw in VS Code here, we install when we typed pip install CPLEX and do CPLEX. So it's two different packages. And I will explain, you'll understand what is the difference between the two by the end of the workshop, hopefully. So first, we'll do some basic modeling with do CPLEX, and then we'll look at more detailed control of the solver. So, for example, we'll look at the log, the different parameters, diagnostics for the diagnosing invisible function and invisible solution models, actually, solution pools, things like that. And finally, we'll look at callbacks, which are something very useful when you want to modify the way the branch and bound works in particular. So the focus will be mostly on solving MIPS. So I won't talk, or linear, also LPs, but MIPs and LPs. I won't talk at all about quadratic programming, for example, or some other type of problem. But I think it will, even with MIPS, it will give you a good idea of how the solver work in general, or how the callbacks also work. So that's why I chose to focus on this type of problems. And besides a few examples at the beginning that are more like toy examples, we will be working around a central example, which is the capacitated vehicle routing problem. So it's a VRP, a CVRP, actually. And I chose this example because it's relatively easy to motivate the use of, for example, lazy constraints or user cuts. So I think it's a good choice for this workshop if we want to talk about callbacks. Okay, so I told you that there is a difference between do CPLEX and CPLEX. So we'll be using both of them in this workshop. So do CPLEX is the higher level modeling API of in Python of CPLEX. So by high level, what I mean here is that it's closer to the mathematical formulation. So as you'll see, we'll be using Python mathematical operators like the arithmetic operator, like less than or equal, plus, things like that, to define the constraints, to define the variables and the objective functions. So it's easier in a sense. It makes like modeling the problem easier than if you have just a function with a bunch of different parameters that you have to know exactly how the parameters work. So this is do CPLEX. So think of it as like closer to the mathematical formulation, closer to the math. And CPLEX is the lower level API. So it controls. Actually, do CPLEX is built over CPLEX, so it calls CPLEX under the hood. And do CPLEX, CPLEX, you can also use CPLEX directly if you want. And sometimes you have to use CPLEX because there is no equivalent in do CPLEX. We'll see a few of those examples during the workshop, but most of the time, I think we can do most of what we want with do CPLEX only. So the language used by CPLEX is it's not as close to the mathematical formulation, so it might be a bit harder to read when you see some code that uses directly CPLEX and not do CPLEX. But sometimes you don't really have the option to use do CPLEX because you're working with legacy code that uses CPLEX directly. And those two, so the do CPLEX and CPLEX, like in the small letter CPLEX here. Those are two Python packages, so they're written in Python, and under so what we call like the CPLEX solver is the software that's written, used to be at least written in C, and that we call through those two APIs, to CPLEX and CPLEX. But we will, in this workshop, so what we will be doing is we write some code, so the application code here in the diagram, and we call do CPLEX most of the time, or maybe directly CPLEX, and those two interfaces will call the corresponding functions, API functions from the CPLEX solver, without you being really having to know about it. Okay, so other questions so far? So feel free to interrupt me if you have at any time during the workshop if you have questions. Let's first talk about the general workflow of do CPLEX. So in do CPLEX, you want to you first create a model. So we'll look at an example in VS Code in a few minutes, but let's just look at this code snippet right now, and just to understand the general mechanics behind creating a model in do CPLEX. So first, okay, we import. So you have to import the right functions or the right objects from the do CPLEX library, which is the line from do CPLEX NP model import model. So, and then on the next line, we create the model. So you create an object in Python that corresponds to the model, the mathematical model that we want to construct. Then we have to build a model. So here, this means adding some variables, adding some constraints, and adding an objective function. It doesn't have to be in this order. It can be the orders here in step 2 does not really matter. You can create the objective function first, the constraint first, however the way you want. So those are lines you can see here at 2A, 2B, and 2C. And then we solve the model. So here we start a solution in SOL. And then we read the results. So there are some functions, some methods that are associated with the solution that lets you read the results. Okay, so let's try to construct this model in Python with do CPLEX and to solve it using the functions that we just seen. So here, so this is just it's very simple model. It's an LP model. So here the variables x1 and x2 are continuous variables, and we have two constraints that are explicitly written here. So what we want to do is simply to model it and to solve it with CPLEX. So let's go in VS Code, and let's create a new file that we can call, for example, example do CPLEX.py, and then we import, as we saw. So I think it was model. I really forgot the import. Okay, yeah, model. The import model. So this imports the class model that lets us create the model objects. And then we can here on the left-hand side, it's the name of the variable. It's common, I think, to call it either like M or MDL. Here I'm going to use MDL for model. This is the notation that I chose to use for this workshop. But you can really use any name that you like. It's just a variable. And then we have the model, and we can associate a name to the model. You don't have to, but it's here. I don't know how I remember what okay, small LP. Just to stick with the same name as in the slides. And we can pass also another parameter, which is about the log output. As we'll talk about the log a bit more in detail later, but you can specify if you want to see the log when we solve it or no. For now, let's just set it to false. False is also the default value, so we didn't really have to mention it here. If we omit this parameter, log output, it will simply be, you won't see the log appearing on the screen. But here I added it, and we can switch it to true to see the difference. So great. So we have the first line, which allowed us to create the model. Then the second step is adding variables. So the function, the method used to add a continuous variable is simply continuous var, and it takes as the model, it takes a name. So again, we can either give to it a name or not. And we can also specify bounds, upper bounds and lower bounds for the values of the variables. So here we see that x1 is between 0 and 4. So we can specify using LB, the lower bound, and UB, the upper bound. So here 0 and 4. And now we can do it with this defines our first variable. And also the variables, you don't have to assign them to necessarily like to a Python variable, but it's here it's convenient. You'll see why. Yeah? So this function here, continuous var, returns an object, which is a Python variable. If you don't, here it will be convenient to when we'll define the constraints, because we'll refer directly to this variable. But we could also use directly the name here. Here, notice I use the same name x1 for both, but actually this one is a string and this one is the name of a variable. So they're not exactly the same thing. Here I could have written any other name and keep x1 here. They don't have to be the same name. But it would just make things more confusing to give them different names. So I stick with the same name. So then we create x2 now, and x2, you see, it's x2 is non-negative. When it's non-negative, you don't really have to specify the lower bound or the upper bound, because by default the value of the lower bound. So let's look here. On this slide. So this is where we define the continuous variables. So by default, the value of the lower bound is 0 and the upper bound is none, but none here means that it's non-restricted. So it could be, it's infinite in other words. So you see on the slides here, I didn't define LB for x1 because it's 0. I could have, here I decided to add it, but it's not mandatory actually. I could have left it out. Okay, so now we have the variables. So let's add the constraints. So again, we call the functions to add the constraints directly on the model object. So add constraint. And the constraints are, so the first one is 2x2 less than or equal to 12. So 2 times x2 less than or equal to 12. So we can go on the next slide here to see how it works. So 2 times x2 less than or equal to 12 is the first argument that we pass to the function add constraint. And the second one, it's the name. Here, it's CT name, the name of the parameter. It's not simply name, so it's constraint's name. It's a bit... I'm not sure exactly why they choose to add the CT in front of the name, but there must be a good reason. So you can give any name here like C1. It's not as important here. This name, I would say, is less important than the name of the variables, because here what's important when we define the constraints, that we to understand is that we refer to the variables that we've added to the model before. So that's why here I decided to assign the new variable that we constructed to x2. It's because we refer to it afterwards. But for the constraints, I could have written, for example, CT1 like that, but it's not very useful because we won't be reusing it later. So we can simply add the constraint and to the model without storing it in any variables. And then we have 3x1 plus 5x2 is less than or equal to 25 times x1 5 x2 less than or equal to 25, and we give the name CT2. Okay. So far, so good, huh? Yeah. Oh, it's C2. Yeah, thank you. But as I said, it does not really matter. It's important if you want to look afterwards when you look at the model. If you want to print it, you will see the name of the constraints, or if you want to do some operations on the constraint, but we won't be doing any right now. So okay, so as you may have noticed, so here we've been using only Python operators. So like the Python multiplication operator, the less than or equal, sign, the plus. So that's what is nice with do CPLEX is that you can use directly the Python operators, which is not the case if you use CPLEX, the CPLEX package directly. You won't be able to add constraints or variables in such a simple way. So that's why it's when you can, in my opinion, it's better to use do CPLEX. Also, we could have added the two constraints in one call with the add constraints here. So it's just that we would have then we would have to pass a list instead of just one constraint. And I'm not sure. I think we can give also the names, a list of the names of the constraint. I didn't mention it here, and I'm not sure how. What is exactly the right parameter to pass a list of names. But as I said, if you don't define a name, the name is not mandatory. It will, CPLEX will would give a name to the constraint by default. Okay, and then the last part before solving is to add the objective function. So we have the choice between maximize and minimize. So here, I think it makes more sense to use maximize than minimize in this problem, and that's how it was defined as well. So we have the maximize 3x1 plus 5x2. x2, and that's it. So this is simply the objective function. And now we're ready to call the solve function. So the last step. So let's run it. Huh? Okay, so it ran, but there was nothing showing up on screen. That's normal because we didn't read the results. So there's, if you remember, there was a last step here, which is to get the value from the solution, the value of the variables. Here, in order to read the value, we have to store the solution in a variable that we call here sol. And then we have to call a function get value on the variables of the solution that we are interested in. So for example, x1. So let's add some print statement to print the value that we want to see. So x1, and let's copy paste and do the same with x2. Okay, and if we run it, then we see the optimal solution. So x1 0 and x2 is 5, according to CPLEX. Now let's try to toggle the value of log output to true instead of false, and we'll see what happens. So here it's a very simple model, so there is not much going on, but you see we have some more information. So we have some information about the version of CPLEX that we're using, some other stuff here about the parameters, and information about what is going on. So we have LP pre-solve, and actually the problem is so simple that the pre-solve solved it directly. So the pre-solve is some kind of, I will talk a bit more about this later, but it simplifies the model. But here, since the model is so simple, it could be, we didn't really have to run the simplex algorithm. But we'll see more less trivial examples in a few moments. Okay, so and we can also see other information about the objective value. So here I showed how to use get value, but we can use get objective value if we want to see the objective value. Let's just do this one. And we see the objective value is 25. And there is also information about that we can get about the status, the solve details. So one interesting one is the status. So was it able to solve the problem or not? So is it infeasible, for example? So here we have, it's not on the solution itself, it's the status of the model. So we have to call MDL status, and then, no, it's not status, it was solve details, I think, yeah, solve details, status. That's right. So we see here it's optimal, as was expected. Okay, great. So that's it for the first model, the first introduction to how to use do CPLEX to solve an LP problem. Now, what if you want to if you're not really interested in the LP problem, or you're interested in an MILP problems with integer variables, or with mixed integers, or mix between continuous and integer variables? All you have to do actually is just change the type of the variable when you create the different variables. So here, if you remember, we were using the method continuous var. But if we wanted instead to have integer variables, we would just replace the word continuous with integer. Here it doesn't really matter that the solution is already an integer solution, so we'll get the same solution. But in general, if you have a more complex problem and you have the LP solution is not is fractional, then by replacing it with integer, you will have an integer solution. And then you see that the log is a bit more complex here. Probably, I'm not sure exactly why, because the solution with the LP of the LP was already integer, but it did some. Actually, we see. I will talk about this later as well as the log of the branch and bound. But you see that there's more information, because usually when you solve a MIP, you have to go through branch and bound. Here we stayed at the node, the root node, but in general you may have to branch. Okay, so other questions up till now? No? Okay, so now we saw how to create variables one by one. If you had a lot of different variables, or variables that are indexed, for example, we'll see like later, we will have a graph and then we have some arcs, and the size of the graph might depend on some, let's say, CSV file with the information about your graph. When you program when you develop the model, you don't necessarily know how many variables you have, how many constraints. because it depends on some input data. So in this case, what you could probably do is just you could put this into a for loop and then create them. But there's a more convenient way to deal with many variables, and this is by using some variable dictionary. So var dic here. So here it's there's an example of how we could use it with a binary var date. So what happens that you pass, you create a list, for example, here of items A, B, C, and D. So you pass this list to the function binary var date, or it could be integer var date or continuous var date, depending on whether you want to create a binary integer or continuous variable. And then you give a generic name for those variables, so select, which will be indexed by the name of the items that you pass to it. So this, what happens that X, then you have X is not just one variable. X will be a list of variables. And the list of variables is here, for example, XA, XB, XC, XD. So you can access the different variables as if you were accessing a Python list. So it's the same notation. So let's look at this example. So this is a knapsack problem. So I'm pretty sure that most of you are familiar with the knapsack problem. If you're not, it's relatively simple. So suppose that you have n items and that you want, so each item has a given value and a given weight. And you want to select as many items as you can so that you can maximize the total value of the items that you select, but there's some capacity that you cannot exceed. So there's some weight capacity here that the sum of the weights Wi cannot exceed this capacity. So the way to model this problem is it can be modeled with this binary, so this MIP, or actually this a binary problem. It's not even here. The variables are all either 0 or 1. So X represent Xi represents the action of choosing choosing the object I. So if it's 0, you don't choose it. If it's 1, you choose it. And then the max function tells that we want to maximize the sum of the values of the objects that are chosen. And such that here the constraint, it's the weight constraint, the capacity constraint. Sorry. So here let's code this quickly. So just that. Okay, so we have a list of items. We can call A, B, C, and D. And we have some values that we can store in a dictionary, or could have been a list as well. But it's I think it's easier in Python to use dictionaries for this kind of for storing this kind of values. So yeah. By the way, I didn't ask, but are all of you familiar with Python? Yeah. Okay, so I will trying to use very advanced features of Python. So it's not a course of a workshop on Python itself. So mostly if you know about imperative programming in Python, it should be sufficient. There will be when we'll talk about the callbacks, there will be a few. We'll have to create some classes, but it's very simple. The use we make of classes is very simple, as you'll see. You don't really have to understand every details. So okay, so the value is a dictionary with 10, 20, 15, and 25. 10, 20, and 5, and we have the list of weights, which were 5, 8, 3, and 12. Okay, and so this was just to define the data, the input data, and now we create the variables using using. So here, yeah, I think it's better to create a new model. So let's I omitted this step in this slide, but we suppose that we create a new model. So let's call it, for example, model knapsack. So you see here, it's not simply MDL, the name of the variable. It's also MDL with something else. Okay, so we said binary verdict. And so we pass the list of items and we give some name. So the name here is select, so the objects that we, so it tells whether we select the object or not. And the rest is just what we did before. So like in the previous example. So we have to create a maximize the objective function, which is a maximize, and add some constraints. Oh, but here, yeah, something first, I think, yeah. Well, something important to mention is that when you have a binary verdict like this one, oftentimes what you will want to do is to you will want to take a sum over some index. So here we take the summation. A bit like when you have like a sigma summation here, you have some index set over which you take the summation. And so we cannot really write them one by one. Here we could do it because there are only 4 elements, but just saying that if we had, for example, 1,000 different elements, 1,000 items, we could not write every single like plus and multiplication operators. And also, if you don't know in advance the size of the items list, you cannot do that. So that's why we use the sum here function from the model. And the sum function takes some, here it's a list comprehension, or it's not really a list, but it uses like the comprehension notation of Python, so with the 4i in items. But it's even if you're not really familiar with this particular notation in Python, I think it's easy to understand because it looks like the summation notation in mathematics. So here we said that we wanted to have the values indexed at I times X. So if we choose it or not, I didn't create X here. And for I in items. So what it says is that we take the sum of this product, so the values of I times Xi, and we take the sum over all the items. So you can think of this as what you would have under the summation, the sigma notation here for the summation. Here I didn't write the full, I just wrote the index, not the index set, but it would be like items here, if you like, under the sigma notation. And so that's how we create the maximum the objective function. Now we have to add also a constraint. So the constraint tells us that the sum of the weight times xi is less than or equal to 18. So we will use again the sum function. So, but here with the weight. So weight I times xi is for I in items. So this is the same. We take the summation over the same index set. And this entire sum here has to be less than or equal to 18. The way. So that's what was defined. What is defined here? Here W. I could have created a variable capital W, but I just hard coded it in the constraint. And we can give a constraint name. I think it's a good practice to do that. Capacity. Okay, great. And now we can we can solve it as we did before. So and let's print. I don't know how I. Yeah, okay. Here we can print create the list of the solution. So let get value of I. Sorry, x xi for I in items. And we simply print it. Have maybe some formatting. Some solution. Okay, and so okay, so here there are maybe should add some just to mention that we're working on the knapsack problem. Okay, so here since the log is we didn't mention anything about the log output here when creating the model. So it's by default it's at false. So that's why we don't see anything else besides the solution. So, but we had the solution here. Let's just set so the log output to true. Okay, see what happened, and then we have some. We see that CPLEX has done some work and figured out that the optimal solution is this one here. So A is equal to 1, B 1, and C 1. So we selected A, B, and C, and we didn't select D. So here, yeah, I could have if you write it this way, I'm not going to do it, but what it does that it shows you which values are bigger than or equal to 0.5. But since we're in a binary, X is a list or a dictionary of binary variables, then in this case, it's either 0 or 1. But the reason why we don't or maybe I should do it actually. Let me, I think it's important to talk about that. So, let's change this. Okay, so what we did here is that we said, okay, look into all of the items and keep the I such that the solution, such that the value associated with I is bigger than 0.5. It's better to use bigger than 0.5 than saying something like that is equal to 1 or 1.0. Here it still works, but there's no guarantee that it will work in general. The reason is that CPLEX uses floating numbers, even to represent binary variables or integer variables. So you will, so when we reprinted the variables, it was not written like 1 or 0, it was 1.0 and 0.0, which means that it's really using a float number and not an integer. And so in general, it's better to use, you can use a epsilon, but in the case of a binary variable, it doesn't really make sense to use like an epsilon. You can simply write if it's bigger than 0.5, then it's 1, and if not, if it's less, then it's 0 in general. So yeah. So that's it for this model. And one thing that you can do when you write a model is you can inspect it. So with the function, the method print information, so it tells you information about the model itself. So let's see what we get when we call it. So you see here we have the number of variables, which ones are binary, integer, and continuous. Here they're all binary. Number of constraints, maximization. It's a MILP problem. Yeah, here I won't do it just because we have a lot of material to cover, but you can have, once you created the model, you can actually, if you're interested, for example, in what is the objective function, let's say that you have a function that creates some model somewhere and it returns only the variable MDL, and you're not sure exactly what it's like, the model, you didn't really code it yourself. Then you may want to see what is the objective expression or the objective function, what is the number of variable, number of constraints. So there are different methods like that, or parameters that you can call, properties that you can call to have more information about the model. This is by no mean exhaustive here, an exhaustive list of what you can, of the parameters that you can get. There are many more, so you can Google them or go to the documentation or your favorite AI and ask what is the information that you can get from the model object. And also, yeah, I think I will mention this quickly. So when you have a model, you can export it. This is also something interesting. You can call some functions. So there are here, I think the most interesting ones are LP and MPS, which are standard formats for linear programs, and in general also MILP. And what you can do is just you call a function with call it model.lp. So the .lp here does not mean that it's continuous. It's just the name of the format. It's a standard format, and it will create, if we call it, it creates some LP files. So we have it here. And this is, maybe you've worked with this kind of file before, but it shows you the model in human readable format. Relatively, let's say, human readable format. And you can also create an MPS file, which is another format available that is commonly used, not only with CPLEX, but also with other solvers like Groby, and I put a list here like Express, GLPK. So I think most of the commonly used solvers would be able to read those two formats, LP and MPS. And the biggest difference, I think, between LP and MPS is that first, so LP is easier to read, as you can tell. So maybe you're wondering why would anyone want to use MPS if LP is easier to read? The reason is, as far as I understand, is that the LP model does not necessarily respect that does not preserve the full numerical precision of as I told you. So all the variables, even if they are integer, they're represented by floating numbers. So if you use LP format, you may have some, and you want to reload it afterwards, you may have some errors in some cases, which is not the case with MPS. So MPS is probably a bit more robust than LP. And to load a model, what you have to do is you import the model reader, and then you just create the model with model reader.read. So you have let's import just one of them. So let's say the LP, and then let's create the variable model LP. And now we can solve it again. And let me copy this. What's this? So we should let's write LP here. So we should have the same solution if everything worked correctly. Oh, not sure exactly. Oh, okay, it's the X. Yeah. Yeah, here it was not. It was created with the other variables. So let me see. I think we have to. I would have to use directly maybe the name of the. It's a bit more complicated when you want to read the variables, but let's just print one of them just so that you understand the general idea. But select A. I think that's what. Oh no, it's first S is not capitalized. So hopefully this will work. Yeah, okay. So it may be a bit more complicated when you create a model. You cannot reuse exactly the same objects that you created before. So here we created the X dictionary binary var dict, but from the MDL knapsack model. And here it's not the same model. It's the model that we loaded from the file model.lp. So we cannot really mix both directly. So when the model is created here, maybe there is another way, but here I think the one way that would work is to refer directly to the names of the variable used in the file. So here you see it created. I don't know why it yeah, okay. It created so solution LP here. It's not LP actually, but let's say it's select A. So we select A is at one. Okay. Okay, and here is a list of some of the functions that we've used here, or it's just a summary of the API. Yeah, but I won't spend time on that unless you want me to. And now we can start talking about the main, the central example of this workshop, so the CVRP. So before we get there, are there some questions about the do CPLEX or whatever? No? Okay, so far so good. So how many of you already know what this like a VRP is, CVRP is? So can you just raise your hand if you've heard it, like if you've seen something like that before? Yeah. Okay, thank you. So I can see that maybe half of you are already more or less familiar with it, which is good. So we won't get here we will the emphasis will be on CPLEX, not on the mathematical model itself. So even if you don't understand every single equation or exactly like the precise formulation how it works, it doesn't really matter. The emphasis is really on how to, with CPLEX we can use. Suppose that I give you some model and you don't really need to understand what it is. How can you implement it in CPLEX? So you can think of it this way. But just to give you an idea of what is like the vehicle routing problem, the CVRP. So we have a depot where we have some vehicles. For example, here on the right-hand side, there's a diagram where you can see the depot, and there are 3 vehicles, V1, V2, and V3. And we have 8 customers that each has a demand QI. It's the value of the demand. And we suppose that they are in a 2D plane, so we use a Cartesian distance calculated by the hypotenuse between like triangle formed by the points. And so the goal here is we want to serve all the customers, but knowing that each vehicle has a capacity of a big Q here, capital Q. So a solution of the CVRP would look like that. So you have a graph here where you go. So a vehicle, for example, if you look at the green line, so we have it goes from the depot, then node 4 to 3, and comes back to the depot. And you have then another vehicle that just goes to node 8 and comes back to the depot. And you have the third one, which is represented by the blue lines. And so every customer is visited exactly one. The total demand on each route has to satisfy the capacity, so it's less than Q, less than or equal to Q. And the goal is to minimize to find a route that would minimize, or the routes in plural that would minimize the total distance. So this is a relatively hard problem. It's an NP hard problem. So when you have bigger instances, it's not trivial to solve this problem. And usually, so you can solve it using some heuristics. But if you want an exact methods, usually what people use is the branch and bound or branch and cut. So branch and bound to which you add some cuts. With the branch and bound with the LP relaxation, so the usual branch and bounds that we use to solve mixed integer linear programs. And so here is a formulation of there are multiple formulations, so this is just one of them that I chose for this workshop. So what it says is that, okay, so Dij is the distance between nodes I and j. So we want to minimize the distance of the route. Ij first, I should have mentioned that, but on the graph here, so suppose that we have a complete graph where we have some arcs between all of the nodes. I didn't draw here the complete graph, but suppose that we have like arcs between all of the nodes. And the variable xij represent each of those arcs. So it means that there's an arc between node I and j. So when I say here xij is in 0 or 1, it means if it's 0, then we didn't choose this arc in the solution, in the root. And if it's equal to 1, then we chose it. And so when we take the sum of Dij times Xij, what we end up doing here is calculating the distance between I and the distance between the nodes, the distance that is traveled by the vehicles on the route. So the goal here is to minimize the distance. So that's the first line. But we have some constraints. So we have some degree constraints that ensure that each customer is visited exactly once. So which are the first two constraints here. And then we have also some depot constraints that ensures that we have exactly k vehicles going out of the depot and coming back to the depot. But if we use this formulation only, we're missing something. So this does not, if you look long enough at it, you will realize that it does not prevent disconnected subtours. So what is a disconnected subtour? So here is an example of a solution to this formulation that is not really a solution to the CVRP problem. The reason is that we can have something like what happens between nodes 6 and 7. So between nodes 6 and 7, you see it's not connected to the depot. So when it's not connected to the depot, it's called a disconnected subtour, disconnected tour. And so in order to solve this problem, what we have to do is to add some extra constraints. One of them, maybe you're already familiar with it, is the MTZ, subtour elimination constraints. If you've never seen it, it doesn't really matter. I mean, as I said, it's just think of it as just a mathematical model that we want to solve. But just to give you just some intuition behind it. So the idea is to introduce a new variable, an additional variable, which is in general, it can be, it's a continuous variable, and it corresponds to the load of the cumulative load when leaving the customer I. So we create UI for each customer, and we add this kind of weird inequality here, or inequalities here that are more than one. And but this inequalities, if you look at what happens when xij is equal to 1, then it forces uj to be bigger than or equal to ui plus qj. So which means that uj is bigger than. So if we go from I to j, then we have to add the demand of j to the cumulative load of at node I. So this is like the intuition behind it, so that we can, if you cannot really come back to a node. If you go like from 3, 4, 2, you cannot go to 3 again, because U3 is less than U2, and it will not work. So this prevents cycles. But also another problem that I didn't mention with this formulation is there is no mention of Q here, of capital Q. So there is no enforcement of capacity here. So this constraint, those constraints, the MTZ subtotal elimination constraints, they both prevent cycles and also enforce capacity. So we will add them to the model. So let me create a new file here, and I will ask you to, I will give you some time to try to model it by yourself using what we saw from CPLEX. So here, so that we don't like waste time just constructing the data set. There's a file called data.py. So you can copy paste, or even if you prefer, you can write directly in this file. It will work, where I define all the data that we will be using. So you've probably noticed that there are some instances here. So later I also created a function that essentially will has that creates the model for us. But since the goal here is to practice the creation of the model, we won't use it for now, but we will be using it later to test different instances. But for now, what I would like you to do is to try using this information. So here, those are the coordinates, the list of the demands, including here, including the depot demand, which is 0. So and you have a list of nodes. So the nodes, it goes from n here is equal to 8. So there are 8 customers. So it goes from 0 to 8 included. So the 8 customers plus the depot. And you have the list of customers, which goes from 1 to 8. So we exclude the depot here. And this is just some function we use here, the hypotenuse function, to calculate the distance, the Cartesian distance between the nodes. And then this defines the arcs. So I'll give you maybe 5 minutes to start writing like the models, and then we'll look at it together. So let me, or at least maybe the first part here, you can try to model this one, and then we can add the MTZ constraints. Or actually, now that I think about it, I look at the time and it's already 2:17. So maybe we can take a break, and you can take like let's take a 15-minute breaks, and maybe, or let's say 20, so that you have 5 minutes more to work on this problem if you want, and then after the break we'll look at it together. So that works with you. Also, yeah, Karen asked me to ask you to write your name on this list here. So don't forget to come and sign just to see who attended in person and who didn't attend in person. Sure. Oh, I can come.
And then, yeah, this doesn't come. It's I don't see that. I don't know.
You install to judge it. I have installed. So what I did. Okay.
Then see, you can try it. Just try it. This kind of try to really works.
Let's see if it's installed. No, it's okay. It should be fine. I think the problem is that did you create a virtual environment? Is it? I'm not sure if it's inside of the environment. Maybe.
Problems. I mean, myself.
Okay, so you would like to run this file. So let's.
Après, ça peut aussi, c'est possible que tu puisses être maintenu en poste. Oui, oui, mais il y a déjà des gens qui ont gradué pendant leur temps.
On lui a parlé, on a essayé de le prendre. Essayé de lui donner le poste là-bas.
Okay, I think it's just like the play button might not have been configured the same way as it is in previous books. But it's just that you have to, the way that you have to call it is like that, so it's not as convenient as the beginning of the development, but you have to type Python and then the name of the script that you want to run. So, yeah, no, I like that. Just this line here, so Python, and then I'm not even sure if you maybe you don't have to leave this. You just write. Here you see you're in the SRC folder. Yeah, so you have all the scripts here. For example, if you want to run this one, let's describe this one. So what you do is that you type Python, so it says that you use a Python language. And then example, yeah, and then you can press tab usually the company's name. Then you just type enter, and you simply get it from. And you don't really need to write a dot and the slap backslash. Just the example. You don't feel it's not necessary here. It's because I completed it and Windows or. I'm not sure, is it? Sometimes it depends on the OS, but for you, maybe there's a way like the problem is that for some reasons it sees like different virtual environment sites. And I'm not sure if you did the thing with the PCA, but I did at the beginning.
I did it, but I didn't know what happens. I mean, honestly, I didn't like
so maybe we can try to
En fait, pas si c'est que ça, je me suis juste mis dans un genre juste faire oui. Je sais installer sur ta PC d'installer sur la version qui prend la protesse en fait. Et je sais pas exactement comment
it's because when you use Python, if you don't create a virtual environment, so VNV stands for virtual environment. And what happens is if you don't create it, it will install all the packages and your global environment. So this means that if you start a project and you install the CPLEX and the global environment, you will have it installed there as well. maybe you may be thinking that that's a good idea, but I don't want to install it every time, but sometimes you may have some conflicts between packages. Or here, for example, you're using a specific version of Python and you want to use a different version in another project. So it's usually better to just practice, create.
Another version of the Python and the
Necessarily, if you have only one, like Python 3.14 or whatever, it's still a good idea to create a virtual environment because you don't always use. Yeah, it's true that here I specify the version, but if you don't, you have, I don't know, by default, 3.14, let's say, you don't have to specify this here. You can write just Python or maybe PY. Now after that, you have to, you see here, it should be created. I don't see it, but.
Yeah, we environment is why twice?
Oh, okay, the first one is the function. It says, the function calls virtual environment. And the second one is the name. So I think on my README file, I use .g, so that creates hidden folder, but it doesn't matter. We don't have all the rules.
But you use by the way,
It's almost the same thing as yeah, so this is the activate, so that's what we're doing right now. So as you created it, so here I just checked that it's created. So now what we have to do is to activate it. So you go in the BNB, then you have
Voilà, c'est le voisin. C'est bah.
and what the
minimum
Ah bah oui, ah bah attends, c'est même pas
I don't know, here it says that you're not allowed from, maybe you have a root access.
like personal lab.
Personal lab, okay.
There's no restriction.
Okay. That's strange. For some reason, prevents people from
Tu sais que dans le monde critique, ça va être contexte. Mais
yeah, so yeah, I'm not sure how to solve this problem because there's something about the active access authorization. So I think that you maybe for now you can probably the easiest
My laptop, it just let me.
yeah, maybe you'll have there are some parameters that you for some reason they were by default that you cannot run some scripts. I'm not sure. With Windows 11 or what do you know like which version of Windows? It's Windows, I guess. The OS here. Maybe I'm not sure how to check the version and ways, but yeah, so I don't know. I think it's a bit unusual, but maybe you once you be able to run like a run script, you can just call this and select the virtual term. But here it works. You see you install the CPLEX in the global environment and it works. So what you have to do is just decide the name of the script.
moi c'est comme la.
And you set tab. So if you start right, that's really like S2 here, for example, start tab, it looks at the minute file. And this one should work. Okay, this is normal because we have not talked about it yet, but we will have to install
Ils avaient plus que. Ils ont fait des papiers, et là, c'était en règle.
Ça serait juste paradoxe. Les personnes jeunes, c'est là où il y a le plus de personnes qui se rappellent.
C'est ça, à partir de 6 heures, là,
Si je ne plus, on s'entend.
à cette place-là, ils se tapent.
Oh, wow.
Ouais, c'est ça, ça fait qu'ils m'ont dit hier.
Mais de rien. C'est
Avec du café. Il y a une Aux alences, là. Donc, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. C'est quoi le OK, parfait. Vas-y, Karine, c'est moi qui ai envoyé les courriels avec Nadia. On vient de partir là. Donc, ravi. Donc, on peut dire l'instant ici au Gérard, c'est pas dur.
Ah non, non.
Okay. Ah ben merci. Merci d'être venu au Gérard. N'hésite pas à écrire au séminaire du Gérard. J'ai des connexions. Je pense que le Gérard.
Merci pour organiser.
Il y a une idée. De maîtriser encore. T'as vu quand cette personne s'est inscrite, on est peut-être 5. On dit qu'ils n'allaient pas être là, qu'ils allaient être en ligne. Donc, moi, je disais, je me suis dit, est-ce qu'il va en avoir 23? Donc, là, c'est pas beaucoup.
Donc, franchement, on va voir. Ouais.
Je suis sûre que dans mon appel, on est. Ça fait pas une connaissance. Ça fait pas mis, là. Au moins pour pas qu'il lui peut la voir. C'est personne, mais vous voyez, c'est beaucoup de monde en ligne.
Je me sens bien. Je sais
C'est tout comme un YouTube.
Et après, je sais pas si vous faisiez exactement la
Ouais.
Le Gérard est appliqué à tout.
Pas beaucoup, excuse-moi.
Le Gérard, c'est-à-dire que.
Puis, je vais faire les exercices. C'est comme regarder un film, regarder son Facebook, puis son Instagram, puis répondre à des questions.
Et en fait, traverse au milieu des deux morceaux de commence.
C'est correct parce que le système l'a partagé sur les journalistes.
Jusqu'à la
Mais pour les deux autres, là, les 13 autres là, qui allaient faire présentiel.
Centre-ville,
Moi, je fais.
Et puis,
C'est-à-dire, je ne sais pas si pour leur dire que la réaction est par c'est ça pour préparer un temps de
Un peu, ouais. En fait, c'est que il y a déjà les mais en fait,
je pense que CPLEX, c'est pareil, un peu plus. Comme si la version 22.1, quelque chose, donc c'est je peux parler pour les c'est ce que je
ah oui, non, c'est juste qu'il y a plus ah oui, oui, des solutions. Je sais pas. Ouais, ouais. Oui, par le accès et l'équation ici. Ah oui, c'est pas c'est juste que je voulais c'est juste ajude
Did it work?
Yeah, it works, but I mean, the same as I just typed the Python sentence. This is solved.
Yeah.
And then, I saw that you wrote another, I mean, that we can see the equations there. I mean, this code as equations. I don't know what did you open? That is, you remember what I mean? I don't know.
I'm not sure that you mean this.
Yes, I was. Yeah.
Yeah, so this is when you export the models, this is like LP or XPS. So here it's not the descriptive example, I think it's one of the previous one that I added like the export function. So this is if you want to export your model once you
Right. Yes.
Yeah. I think it works. It's doing something. It's perfect. Maybe there was.
Just this, you know, that should I fix something in my laptop that I solve this problem that I have?
Yeah, you should. I'm not sure exactly. It's something in Windows probably that prevents you from running scripts. Yeah, I'm not sure you Google it. I'm not an expert in Windows, and
Thanks so much.
I just don't know what. But it seems to be like some authorization, or maybe it's when you open VS Code, you open it, and you don't have the double drive, the authorization to open it. I'm not sure exactly. You can try, and if you're able, and if you, for example, if you run the PowerShell, those PowerShell. Would you be able, and you can try to do virtual environment and activate it. Sorry, I can see if it doesn't work here. Yeah, so there's something like in Windows in general, but it's just in VS Code. Maybe it's when you install VS Code. Maybe it's you installed it a lot. Maybe you install it like on your documents folder or something like that. It made it maybe during where it's but I'm not sure. Okay, so let's start again. It's been 20 minutes. Okay, so did some of you have time to look to try to model the problem? So I mean, of course the solution is in the slides, so you can just look at the solution if you want. But did some of you try at least do something? Yeah. So did you encounter some problems or while doing it? Was it easy or yeah?
I just have something a little weird.
Yeah.
As I got some zeros inside the roots. I mean, it's further in the slides, but you show you show what we should get as a result.
Oh, okay.
Like expected outputs. And I don't have exactly the same as.
Oh, is it on this slide? It might be. Maybe I updated.
Not this one.
Okay.
33.
33.
Yes, I don't have exactly the expected outputs.
Oh, it's possible. It's possible that it's not the. Yeah, it might not be like the expected output. Actually, maybe I modified the instance. So we'll see. It's not. It doesn't mean that it doesn't work.
Otherwise, I have the same check. So
okay. Yeah. Okay, great. So does anybody else have some question about that or? Let me see. I think online I have some. I see that I have some. Oh, okay. No, that's fine. Okay, so let's construct the model together now. So we'll try to do it quickly because I would like to cover other material as well. So as usual, let's import the model class. And then we will create the MDL. So call it CBRP. And we want to add the minimize, so we can start with the objective function here. The objective function is the sum over Dij Xij. So we have to look at the distance, so the dist here. So we call the sum function. Okay. Oh, actually, I should have created the variables first. So binary var dict. We'll call it x, and it's going to be indexed with the nodes. Okay. Just check I did here to make sure. No, sorry, yeah, it's not the nodes, it's the arcs, because we have one variable for each ij pair, so it's the arcs, of course. And what name did I give them? X here. Okay, and now we have xij. And this sum, so we want to minimize this sum for I, I should have done it. Yes, I did. For ij in arcs. So we have one variable for each arc. So okay, so here I started with the minimize function, but in the slides I actually define all the variables first. Let's do the U variable later. Let's just first encode the constraints that are related to the degree constraints and the depot flow constraints. So for the degree constraints, so what is important is that to notice that we have here one constraint for each customer. So the for all j in C is important here. It's not just, it looks like only one constraint, but actually we have the number of constraints, we have as many constraints as the number of customers. And so we, to deal with that, we take, we create a for loop and where we iterate over the customers. And then we add one constraint for each customer. So the constraint here, it's again the function add constraint. I could probably have used add constraints with an S and so constructing. I could have constructed the list of constraints and then passing it only once, making only one call with add constraints. But I think it's that doesn't really matter here. I think it's easier this way. And so we create the sum. The summation is over xij. Now j is fixed, so it's going to be over I in the nodes. So we include as well the depot, so it's not only over the customer. And we don't want to add a variable if I is equal to j, because they correspond to the arcs. Essentially, there is no II, for example, xii. So it's if I is different from j. And this equal to 1. Okay, and city name is equal to in j. F. Okay, great. So the other constraint is very similar to this one. So let's just copy paste so that it goes faster. And then we have I in customers. So now it's for all I in C. And this is the all degree constraints. So we fix I, but we take the sum over j. So out. Okay, and then we have the depot flow, which is only one constraint at the depot, so from 0 to j, and then from I to 0 in the second one. So let me just copy the add constraint here function. So we said 0 to j, and for j in customers, we don't need this part. And this has to be equal to k, not only to 1, so the number of vehicles, and we call it depot out. And we have similarly depot in, which is I, 0, I. Okay, great. And now let's create the variable u that we didn't create here. So the variable u is it's continuous. They correspond to continuous variables. So we can add u continuous var dict. No, it's mdl that continuous var dict, and then we index them with the customers. And we have some lower bound, upper bound, which is 0. The upper bound is the quantity, the capacity, because it corresponds, as I said, it corresponds to the cumulative load. So it's bounded by the capacity from above. Name is equal to u. Okay, and now we define the MTZ constraints, MTZ constraints. So, So this is the first. So if you remember here, we have two sets of constraints. So the first one is over all ij customers, where I is different from j. So that's exactly what we wrote here. So all I, all j customers, and I is different from j. And then we have to write these things here. So ui minus uj plus q that is q times xij. Let's check. Okay. Then we have the name, city name. Okay, so that's for the first part. Then the second part is so we have this for all customers I. So for I in customers, we add one constraint, which is UI is bigger than or equal to demands I. And city name is ULB and okay. So now it should work. We can execute a code just to see that if we make sure that we didn't make any typo or yeah, I think it works. There is no error message. And now, okay, so we've created the model. We've already added the minimize function. So we can try one thing that we can do before solving it. If we want to see information about the model, we can simply print to see the number of constraints, for example, that were added, number of variables. So we see 72 binary variables, which makes sense. And we have, because we have like 9 nodes, and so 9 times 8 is 72, 82 constraints, so which are all linear, and eight continuous variables for the u variable. So xij, we have 72 of them. Yeah. So great. So now we can solve the problem. So MDL solve. Let's put the log output to true. So I told you that when we can pass the log output parameter, so our argument to the log output parameter of the model, but we can actually pass it also to the solve function. If we don't want to define it as true or false in general, but just for an execution of the solve function, for example. So here, when we solve it, so we see we have some information. We see the branch and bound here, and we have the time that it took to solve the problem, which is here. It's very fast, 0.06 seconds, because it's a small instance. And now we can have a look at the solution. So here, actually, I wrote some functions so that it will be easier to extract the root. So it's not a workshop about Python itself. So I don't want to spend too much time in doing like for loops and just to create the solution. So I already provided some functions. But here, the only thing that is important is to be able to get the active arcs, so the one that were defined to one. So let's copy this. Let's write actually this this line of code here to active to get a list of the active arcs. So we want to have ij for ij and arcs if sol that get value of x ij is bigger than 0.5. So as we did with the knapsack problem, so we want the solutions that are equal to 1, but we use the threshold of 0.5 to do that. And so we have this list, and now we can print it just to see what it's like, but it's not very it's hard to see what does the solution correspond to here. So we see which arcs were chosen, but it's hard to see like what are the different routes from that. So in order to what we have to do is to convert it, so to try to recreate the routes from there. And I created some function here that you can. I think I put it in VRP model, or no, actually. Oh, it's probably there because we will. I provided here in VRP plots 2 functions. One of them, it's not really a plot, but it's to extract the roots. That will then be passed to the plot functions, plot roots function, which uses matplotlib to plot the roots. So let's import those 2 functions. So we can do import from VRP plots, import extract roots and plot roots. And then we call extract roots with, we have to pass 3 parameters. So the first one is the list of the active arcs. Then, oh no, it's sorry, it's for the roots that we have to pass 3 parameters. Here the depot is at 0, so we don't have actually to pass the depot. And let's store the results in roots, and let's print it so that we see what are the roots. So okay, yeah. So because I imported plot roots, so plot roots will use matplotlib. So let's install it right now. So pip install matplotlib. So matplotlib, if you don't know what it is, it's a library to plot graphs in Python. I think it's a very popular library, and so it may take some time to install. So so here, if we go just while it's installing, I can go quickly over what extract roots does. So if you're interested, like in the detail of how to reconstruct the root, you can just look at this the code, or like this code snippet, or the code in the repository. But what it does, that it goes through all the arcs, and then it tries to if an arc is equal to 1, then I mean all of those arcs are active arcs. So it tries to reconstruct the roots from the arcs by using here the while loop. So you go to the next node until you come back to the depot, and then you create the root this way. I don't want to spend too much time on that. I don't think it's very relevant for this workshop. And now let's try it again. Okay, so it works. So now you see the second print here corresponds to the root, so it's more readable. Now we see that we have 3 roots, which makes sense because we have three different we have three different we have three vehicles, so k is equal to 3, so we should have 3 routes at the end. And now let me see if we have exactly 4, 2, 3, 1, 6, 7. Here I have it's in the reverse order, but it's the same as what I had here. So I don't know if you told me you had a different. Is it because it was in reverse order, or is it?
Not exactly. I got some zeros between the nodes of the row.
Oh, so this.
The row, I don't have the roots 0 and 0 there.
Okay. Do you have 3 roots only, or?
Do I have
Do you have only 3 roots in the end, or you have more than 3 roots?
I have like 5 roots.
Okay, so there might be a problem with the way you implemented the depot flow constraint. So the one about this one here for the k, you should not have more than k roots. Or maybe it's the subtor elimination. If you, I'm not sure exactly, but there seems to be. Maybe you can compare with the script that I provided in. If you want to have the full script, it's here. So you can, but there might be some little typo in your model.
Or maybe some lines that I've been returning that shouldn't there.
Maybe.
Probably, okay.
Are there questions so far? Oh, okay. So let's print the let's plot the roots. So by using the plot roots function, so we have to pass roots, and then so what are I forgot demands and cards and demands. And demands here. So, and now we see a graph of the roots. So we see that we have 3 roots, sorry, that all come out of the depot and comes back to each comes back to the depot. Okay, great. So now we have still 1 hour left. So I might go a bit faster on some parts that are not maybe that important. So here we've already done that. So we could look at the status. The status here when we have an integer program like this one. So the status will tell you whether it will be integer optimal instead of just optimal. If you remember what we had with the LP the small LP that we saw, it was only optimal that was written. We have also we could have a look at the objective value as well if we wanted to. But one thing that for the rest of the workshop, so we'll be using, we'll construct the model again, the same model, but using instances from that are generated from the JSON files here. And I provided some functions here. So one functions to build a model. And so we'll import this function and use it to construct the model. But it's the same inside it. It's the same model that we've constructed. It's just that we use different data. Okay, so so let's talk quickly about the CPLEX logs. So we have, let's look at this one here. So here, when you run, when you solve an MILP, you usually have a log that looks like this one. So you have information about the node that it's currently solving, the number of nodes left, the objective function, if it has found an incumbent. So if you found some feasible solution, you have some value about the sorry, no, it's this is the best integer here. This is the objective value of the LP that it's solving at each node. So are all of you familiar with branch and bound in general, or Yeah. So I had a slide where I explained the log. So yeah. So what we have when we look at the log, we have usually one row for at each time that there's some progress made by CPLEX. So it's not so that the number of rows, it does not really depend on some time interval. It's more as if something important happened, then you have a new row showing up in the log. And when you see the node 0 here, it means that you're still at the root node. So that's what happened here. We're at the neutral all the time, so we didn't really branch. When you have what CPLEX does at the time often is that it adds some cuts, so some cutting planes, for example. Whenever you have a new incumbent, so a new feasible solution, you see an asterisk or a star like here. And you have here are more information about what's currently happening. So one that is important is the objective here, which corresponds to the LP relaxation value at that node. So if you're at the root node, it will be most likely the same as the best bound. So that's why you see here we have like the same value for the best bound and the objective. But in general, this objective can be different from the best bound because you may be at another node of your branch and bound. And you have the best integer, which is the best solution that it has found so far. And if you're in a minimization problem, so in general, what happens that the best integer goes down because this is your the best solution that you found so far, and the best bound goes up. And what is the distance between the best bound and the best integer is called the gap. So it's the relative distance here. So it's not like it's not an absolute distance. It's so you essentially you take the bound minus the best integer in absolute value divided by the bound, I think, or maybe the integer. Yeah, I think it's I'm not sure, but it's some relative distance between the bound and the best bound and the best integer. You have also information about I think one thing that is important is also the plus, which tells you that you have that the heuristic found a new incumbent. So whenever even if you don't tell CPLEX that you want to use some heuristics, and by default it will run some heuristics, and you'll see that there are parameters that we can change to determine whether we want to use more or less heuristics during the branch and bound. But usually, if you don't tell CPLEX anything, it will use them by default, the heuristics. Other questions about the log? Something that you would like to know? No? Okay. So here I will also go fast over this part. But if you want to have like programmatically access to the details of the solution, for example, how what is the status, the time, and all, you can have access to each of them. So it's not. I showed you that there's we saw already some of them like the status, but you can have access to most of the details about the solving process. Okay, now let's talk about the parameters. So for the parameters, so there are a large set. There's a large set of parameters that you can modify in CPLEX, and some of them are about stopping criteria, like time limit, mid gap. So we can tell we want to stop after 1 minute, for example, or I want to have a mid gap, a relative gap of, I don't know, 1% or something like that. And then it will stop as soon as you reach one of those criteria. You can also change the emphasis between finding a feasible solution. So it might be using heuristics, or also the way that you do the branching and the way that you do the branch and bound, and also proving optimality or finding the best bound possible. So there are you can modify those parameters. There are also some parameters about the pre-processing, so the pre-solve that I mentioned quickly earlier, and also about the branching. But some of them are more technical, more advanced. So I will only talk about the ones that are the most, in my opinion, the most commonly encountered parameters. So one of them is time limit. So let's say that we want here we have the problem is a bit too small. So let's just create a new file that we're going to call. It's not in the right folder. Here.
Is that option? Initial point to start.
Sorry.
This is just mixed linear.
Yeah.
Mixed integer linear programming.
Yeah.
And so we definitely have the results. You don't need the initial point to get it. Just the initial point to start the run, or maybe that's.
Well, we don't need an initial solution. No? If we have one, this is called a MIP start. So I will talk about that a bit later. So you can provide, if you have, for example, a heuristic that gave you a solution, you can provide.
Sometimes, I mean, this is easy, but it's become big problems.
Yeah.
Especially integer, it become.
Yeah, sometimes it can take hours or days or weeks to solve a problem, but you can pass like a warm start. You can do a warm start with some solution. Yeah, we'll talk about that as well. So let me create the model. So from VRP model, import build model. And then before we do that, we have also to import the data. So from VRP data, import that's something with load instances, load instance. So we had an instance. And here it's in data. So let's say CVRP 15, or maybe even 20, because we want it to take longer. And now let's see if this works. So what we did here is that, so I loaded the instance from the JSON file. Now it's in the object, it's a dictionary instance that contains the different, the important information. So it contains, like it's this dictionary here. So we can access to the demands chords those are the keys of the dictionaries. And we have also the build model function that takes instance as parameter. And we'll see later, if we have time, we'll talk about callbacks. And so I want, for example, if we want to not to add the MTZ constraint, because we may want to add some subtour elimination and the constraints in the callback directly, then we can construct it without the MTZ constraint. And it returns, in the end, at the end, it returns the model and the variables X. That we so that when we solve, we can pass the variable then to the plot function, for example. Okay, so now let's solve it and let's log the output and let's see what happens. So you see now it's solving, but it's a bigger instance, so it's not it takes some time, and so CPLEX does many things here. I think it repeats the pre-solve, and so it does a lot of different stuff here. But since it's taking a long time, let's say that we want to impose a time limit of let's say 5 seconds, because we want to have a solution quickly. So what we do is that we go to the MDL parameters and time limit, and then we fix the time limit, which is in second here. Let's say 5, and then when we run it. You see, it should stop after 5 seconds. So you see, it stopped at 5.03 seconds. So we don't have an optimal solution. So if we look at the status, it should be we should see the solution. Yeah, I didn't, but let's solve. Detail status, and if we print it, we should not see optimal this time. So here it's time limit exceeded. So that's the output of the status. That's the value of the status. Okay, so that's one parameter that we can fix. One stopping criterion. Another one is the mid gap. So let's just comment this one. So let's say that we want to have a gap of 10%. So we have to change this here with so parameters mid MIP tolerance parentheses with mid gap. And now we run it again. So I think okay. So it stopped here after 10%. Here it's not. I mean, we know that it would have taken longer if we didn't set the mid gap to 10%. But we see here it tells us, okay, it's optimal. It says that it's optimal, but it's optimal because of the tolerance here. So for you, maybe it's never by default the mid gap tolerance is I think it's 10 to the -4, which is 0. Yeah, that's what I wrote here, 0.01%. So it's very small, but it's even 0.01%. It's not really optimal. I mean, it's usually considered optimal. But depending on the problem that you have, maybe if for you 5% or 10% would be optimal. And in general, I think it's fairly high, 10%. So you won't qualify this as optimal. But in terms, sorry,
it's a percentage or
this is no. Okay, so you have to write here. This corresponds to 10%. So you have to write it as a floating as a float number. Yeah. So it's 0.10. It means 10%. Yeah.
This is the absolute tolerance at
I mean, it's the relative. It's you see here. We talked about the gap here. So the gap is this value here at the end. So it's the difference between here in this case the lower bound and the best integer. Yeah, so it's relative. Yeah, exactly. So it's not, if it were not relative, for example, here the value, like the best integer is 97, here it's 78. So you would have to provide like some numbers. I think it would not be very practical to have something in the absolute value. So it's relative here. Other questions? Okay. So that's so I think that the stopping criteria are very important to know because usually you may want to fix yourself the gap. Another one that is interesting is the emphasis that I talked to you about. So if you want to emphasize on a feasible solution, so finding some incumbents quickly, then this is used by what happens that CPLEX would use more heuristics, for example, or using some bias in the branching so that you find some integer solutions quickly. But you can also emphasize on optimality, so it will add some more cutting planes, less heuristics, and you can also focus on the best bound itself. If you want to, if you have, for example, you have some solution, but you would like quickly, but you would like to show that the solution is within a given gap, a given distance from the bound relatively quickly. So you want to work on towards the bound. And by default, it's at 0, which is it balances feasibility and optimality. So I won't do an example about this, but you can, if you want to try, you can just switch the different parameters and see what happens by looking at the log. Okay, and so also if you have a look at the code, I think it's S3, this one here. I wrote like a little some function, and you can run it if you like, just to see what happens, the effect of changing those parameters. Oh yeah, maybe one function that is interesting is reset all. So it resets all the parameters to default. So if you have if you don't want like to change once you modified some parameters, you don't want to modify them back one by one, so you just reset them all using this function. Yeah, okay, so this is, we already talked about that. So, okay, let me, I'm not sure if I would like to talk about callbacks, and maybe, okay, there's one thing I won't really do an example about that, but if you're interested, you may go and read about the conflict refiner. So this is like a tool that lets you find if you have, let's say that you modelize your problem with CPLEX, and then CPLEX tells when you run the solve function, CPLEX tells you that it's infeasible. Then you can use this tool, the conflict refiner, to determine which constraints are problematic. So what it does is that it returns some reducible infeasible subset, which is the smallest set of constraints that taken together are infeasible, which means that whenever you remove one of the constraints in this IIS, it becomes feasible. And you may have to run it multiple times. Sometimes CPLEX gives you one IIS at a time, and then let's say you remove one constraint, and then you have a new IIS that may also make the problem infeasible, and then you have to remove another constraint or correct the constraints. Usually, it's not just removing them, I think. It's more like maybe there was in the way you model the problem, there was some fundamental issue. So you can so it's relatively simple. You have to use the conflict refiner class here, but I will skip this part. I think it's the other stuff is more interesting. Okay, let me talk a bit about the MIP start. So that was your question. So when you have, let's say that you have a problem that is relatively hard to solve, sometimes it helps to provide a solution to the MIP. And the solution, it could be, it's usually constructed using some heuristic. And here, actually, I constructed, I wrote a function that finds the nearest neighbor, that solves the problem using a nearest neighbor heuristic. So something very simple. It just goes from the depot and then to the next, to the closest node, and then to the next closest node and all. And when the vehicle is full, then it comes back to the depot. So this is the code for the nearest neighbor. It's in the model. It's here in the VRP model.py file. And so let's create another file example. Let's start. And so from VRP model import nearest neighbor. Okay, and also, I will just copy this here. And copy those lines. So it's the same thing that we did in the previous example. So let's take here 15 instead of 20, because 20 takes a longer time to solve. And let's use, so here, so we build a model as usual, but we can also construct a solution using the heuristic, the nearest neighbor heuristic. So here we pass the list of customers. So it's in instance customers, then the demand, the distance, then and Q, and it should return some solution. I will add HEUR here to specify that it's the heuristic. And if we look at the solution, let's print it. So this is not a CPLEX solution, so it's just here a list of the roots that was already created. So here, if we look, we have 4 roots, so k is equal to 4, so this makes sense. So in this instance, it's not just 3 roots. Okay, so what I want to show you is that we can, how to use the MIP start, how to use the solution as a MIP start. So to use a solution as a MIP start, so here actually I call it roots, which makes sense because it's it's the list of roots that we get usually when we extract the roots from the active arcs from the CPLEX solution. So what we will do here is that we have to import from do CPLEX MP solution an empty solution, which is the class solve solution. And then we create this empty solution that we can call a warm start, for example. And to this warm start, we will specify the values that we want to fix. You don't have to specify all the values. So for example, here I only specify the values that are the important ones, so the ones that are equal to 1 in the problem, and I don't even specify the one that comes back from the depot. So even if you don't specify them, the CPLEX will try to correct the solution. So it will find a solution that is compatible with the model, and so that you can just pass a partial solution if you have a partial solution. If it doesn't work, if you write a solution that is infeasible, or even a partial solution that is infeasible, CPLEX will tell you when you solve it, try to solve it. So let's do this here. So for a root and roots, we want to go over the IDs of the roots. So IDX and okay. And okay, and we add the var value. So this is a new method. So this method, oh, actually, I didn't create the. Yeah, we have to import it. So let's import it first. So from do CPLEX MP, what is it? Solution, import solve solution. Then this is our empty solution that we call warm start. And we have to add some values to the solutions. So what we do here is that we go, so for each route, we go to, we start with index 0s at the depot, and then we look what is the next node, and we go arc by arc, and we set it equal to 1. So X, the X, yeah, IDX, okay, no, sorry, root, it's in parentheses, bracket. Okay, and one. Okay, sorry, this should work. And then let's just run this without the mip start first. No, there's a problem. So solution missing one. Oh yeah, okay. Yeah, when we create the empty solution, we have to pass the model. So I have not created the model yet. So let's create, as usual, the model. I have to port it. Now this should work, yeah. And now we can add the warm start using MDL add mip start. And let's solve it with the log output. Let's run it. Did I forget something? Let me see. I think I forgot something about we have to specify that it's MIT. Oh yeah, no, sorry about that. It's we have first to it's not it's this model that I should use, so that's why I didn't create it. Yeah, I was a bit confused. Sorry. So we created the model. We create the model first with build model, then which creates our VRP CBRP model, and then we associate a new empty solution to this model specifically, not an empty model as I just did. And then we add the warm start solution to the model. And now it's solving. And here, what I want you to notice, we will see, it's hard to tell because it's here it solves fairly quickly. But if you look at the number of nodes, so let's print the number of nodes. So in the solution, let me copy what I did here. Number of node processed, and just copy that. Okay, so what we do here, we look at the solution. The model. Okay, and the number, so the objective value, and what is the number of nodes processed. And we'll do it once with the mip start. We'll look at the value that we get. So here we get, so the objective is this one here. Maybe I'll add it as a comment so that we remember what it is. Okay, and we have this number of nodes here, 34,751. And now let's just not add this mip start to see if it makes a difference. So in terms of time, it's faster. Now, surprisingly, here I think I tested it with another instance, but here we have actually less nodes. So the mip start didn't really help. But maybe let's try with not sure what. Let's see which one I use here. Maybe just A. So sometimes the idea of usually you will want to use that, so the mip start, so that it makes solving the problem faster. But when you have very small problems, sometimes it doesn't help at all. Yeah.
Is it normal that it indicates with mip starts
at
the bottom line?
Oh, yeah. This is just the formatting and the print. Yeah.
Okay,
this is not. Yeah. Or it's here actually, but yeah, I should. Yeah. It makes it's a bit confusing, sort of. Yeah. But let me see this one here. So we used 8. Maybe it will help. But at least we see that we don't get exactly the same solution, because usually if you run twice CPLEX, you will get exactly the same number of nodes and the same objective value, unless you add some randomness if you do some if it's asynchronous. But usually here by default it should be deterministic. So here you see we have, I said we have this for the new. Let's just add it here, and what we have when we add the mid start, then we have a different number which is a bit smaller. But as you saw with the other example, it was actually the number of nodes was smaller with the mid start. So it's not usually like in very small problems like that. If it takes only a few seconds to solve, you may have it. It doesn't always help. And even with bigger problems, a mid start won't necessarily help. It's not a magical solution, but it's sometimes it's still interesting to have to start with a feasible solution. Okay, so other questions so far about mid starts? Yeah.
Question. There's no this MI start file in your file in
You mean you can you have to construct your you can the nearest neighbor is from I mean we construct the solution using some heuristic. If you want, you can you do this, you call this line here from VRP model import nearest neighbor, and then it constructs the solution, which is in the form of roots here. And then you convert it into some empty solutions for the model, and then you can add it to the MIPSTART. So there is no, it's not in a file. You have to reconstruct it using some heuristic. Okay, so I wanted to talk about actually callbacks. I think the solution pools, it's easy to use. I will just go very quickly over it. So in general, when you solve CPLEX will generate multiple solutions. So it encounters, as you saw, like there are some heuristics, and you have the best solution, that the value of the best solution that decrease if it's best integer solution that decrease if you're solving a minimization problem. And sometimes you're not necessarily interested with only one optimal solution, but you may want to have a pool of solutions that you can choose from that are, let's say, within, I don't know, 5% of the best solution. So in order to do that, what you can do is you can, I would say, like activate the solution pool, even though it's always activated, but you can actually look up for solutions in the solution pool, and you can control which solutions should be kept in the solution pool. And that's what the solution, the default solution pool of CPLEX does. So it's here there are actually it's very simple to modify the parameters of the solution pool. So you use it, it's just a parameter. So parameters that MIP pool, you have the capacity, the relative gap, intensity, and the way you would replace a solution that you don't want to keep. If, for example, the capacity of the pool is too small and you have, okay, so yeah, I should explain what is capacity. So capacity is the number, the maximal number of solution that you want to keep in the pool. By default, it's unlimited, but sometimes you may not want to keep all of them. So let's say you have 10 here. Then if you have an 11th solution or a 12th solution, how would you replace those solutions? So this is the parameter replace here. So you may choose to get rid of to evict the worst objective, but you may also decide that you want to evict the oldest one, or you want to have some diversity and you want to keep solutions that are the most diverse. So those are the three parameters that you can choose from. And also now there's also relative gap and intensity. So relative gap tells you, for example, I want to have here all the solutions that have a gap that are at a distance of 10% from the optimal solution. Or it could be 1% or whatever you like. So you have a certain guarantee that those solutions are good quality solutions. And intensity, it's the way how many solutions you will generate in general. So if it's at 0, it's only the solutions that CPLEX finds naturally, which is not that many. Like in those small problems, it may be like just 2 or 3. If you have bigger problems, of course, it will be more than 2 or 3. But if you specify there's 0, 1, there's actually also 1 and 3 that you can choose from here. But it's an intensity, so it goes to 0. It's just natural. Then if you go to 4, it enumerates all the feasible solutions. And in between, like 2 and 3, so it generates more solution. So even with this kind of problem, you may end up with like 30, 40 solutions, for example. Yes.
So you went to the place where we certain more diverse solutions. So when you talk diversity, is it only like the function, or is it like individual?
I'm not sure exactly how diversity works. I would say that it's probably not about the objective function. It's probably a diversity based on the variable, because it would not really make sense. You don't want to have like a very bad solution and a very good one. But I'm not sure exactly what it does. Yeah, that's a good question. You could probably, it's probably fairly easy on the internet to find some explanations, but sometimes as well, they don't, with like commercial solvers like CPLEX, they don't explain exactly how they proceed. What is the exact algorithm to find like what diversity means exactly. Maybe they don't say it as well. I'm not sure. Other questions? No? Okay. So now this will be the last part of the workshop. So I want to talk a bit about callbacks. So I implemented 3 different types of callbacks. So we'll probably have time just to do one of them, but they all work more or less the same. I think what's important for you is to understand what is a callback, how it works in general, and then you can have a look at the other examples in the slides or in the code. So a callback is essentially, it's a function that you write yourself, but that you don't call yourself. So it's you provide this function to some kind of system, here to CPLEX, and CPLEX decides when it wants to call this function. So in the case of CPLEX, so maybe I can go over that like quickly. So usually, so you write your code, you register the callback in the system, then the system runs, and then when some specific event occurs, the system will call your callbacks. So that's in general, that's how callbacks works in programming. But in the case of CPLEX, it's usually it's within the branch and bound. So if you want to have some control over what's going on in the branch and bound, you can pass a callback function that you create, and then CPLEX at different moments. So you have some events here. So this is not an exhaustive list of the events here. I mentioned below some other events like when branching, local progress, things like that. But those are some important ones. So one of them, for example, is at the relaxation. So after you solve, so at each node you solve some LP problem. So at this moment, after solving the LP, so before findings, so no, I mean, at the moment you solve after solving the LP, you have access to some the LP solution, and you may want to add some cuts, for example, some user cuts. I don't think we'll have time to go over that today. But so a user cut is a cut that will it's some constraint that is not mandatory in the formulation of your problem, but that will help the bound to be tighter. So you reject some fractional solutions that would not, since they're fractional, it does not matter to reject them, but you do not reject any feasible solution. So it's usually non-mandatory cuts, those non-mandatory constraints. So then, so this is an event when it's called. Another one is candidate, which means that it's when CPLEX finds a new solution, a new feasible solution, And one use case of that is when you want to use lazy constraints. And again, I don't think we'll have time to cover lazy constraints today, but the idea is that when the callback finds this new candidate, then your function is called, and then you may decide, you write some algorithm that says, for example, I want to add a new constraint that will reject this solution. And here it's important to make the difference between user cuts and lazy constraint, because lazy constraint is really about the integer solution. So it will reject some solution that in the formulation of your model are valid, but that are not they're not meant to be valid, in the sense that your model is probably incomplete. I will just go back to the MTZ constraint that I mentioned earlier, just so that you understand what I mean by that. It's here. So we had this model here without the MTZ constraint, but we saw that without the MTZ constraint, we may have some subterms like this one here. And there's also a problem with the capacity. But let's say that we want to we don't want to implement the MTZ subter elimination, because maybe it's compact, it's not that many constraints, but maybe in some other problems it would be too like you would have an exponential number of constraints. Or here you want to have here I think it's one of the problem with this formulation is that the LP relaxation is not very good, so you have a better relaxation if you use if you implement other with another formulation. So let's say that you don't want to implement those constraints. Then what you can do is that you can say, okay, I'm going to run this model here, knowing that I may have subtors, but when when the callback is called. So at the event candidate, I will check whether there's a subtor in the solution. And if there's a subtor, I will myself say, oh, the solution is wrong. I will reject it. And I will add a new cut. I will add a new constraint to the model that says you should reject all solutions that have this kind of subtors. So this is what a lazy constraint is. So a lazy constraint, it rejects some integers of valid solutions, whereas valid in the sense that they are valid with respect to your initial model, but it's because probably your model is incomplete. But a user cut, it's just to improve the relaxation. Yeah.
So these constraints,
yeah,
these are like checks after you find the solution, and based on those checks, you add new constraints to all the nodes that you will reach later.
Yeah. More or less, actually, we can do. I planned on. I wanted to start with the global progress, the informational callback, but maybe we can do the lazy constraint together so that you see more precisely. I think it might be more useful. So let's do that. But I will hopefully it will answer your question, and if not, you can ask it again. But yeah, so the third type of callback or event here is global progress. It's just like an informational callback that would tell you. I can show you the graph. Actually, it's probably the most important, interesting part here. Is if you run S4, so the script S4, you will see some. You should see some graph here. And this was generated using a callback. So you see what is the incumbent, so the best feasible solutions. So on the right axis, you have the objective value. On the x-axis, you have the time. And you see that the best bound increases, which makes sense when you solve a MIP. And the incumbent, the objective value of the incumbent decreases. So as would be expected. And this was constructed using some informational callback. But let's just go quickly over that. But I think let's do the lazy constraint one. I think it's more useful than the informational one. So the way so this is the general. Before going to the lazy one, let's just see what's the general syntax when you create a new callback. So when we create a callback, we have, I told you that we will be using a bit some classes. So here you have to create a new class that has an invoke method. And this invoke method is actually the callback itself. So it's the function that is called by CPLEX. And I'm not sure, actually, maybe you don't even have to create a class, but this is the standard way to do it. Maybe you can just pass some, no, probably, no, it expects some invoke function. So yeah, anyway, so what's interesting when you have the class is that you can store also a state. You can store information that you can save between the callbacks. One part that is very important is this context object. So you have to create the invoke function with the context object, and then you check at the beginning the ID of the context, which tells you which event you're in at this moment. So usually when you create a callback, you register the callback with self callback, and you specify at which event or events you want the callback to be called. You want the invoke function of this of my callback here to be called. And then, but when you're inside the invoke function, you can check also if you're not in the right event, and you may return. It's not here in this case. It's a bit trivial. It's not mandatory because you already registered it for a single event. But when you have multiple events and you may want to do different actions within the callback, you may want to do this kind of add this kind of if here. Okay, so let's just code the callback for the lazy constraints. So you'll see what it's like. It's more simple than it looks like. So example callback. Okay. And so let's create a class called, I think I call it like subtor elimination, because that's the goal of this callback. And as we said, there is invoke function, invoke method. So since it's a method, it starts with self, as usual, and we have the context here. So what we want the callback to be doing is, here I will go very quickly over that, but actually we'll just implement some new constraints inside the callback. They are called the DFG subtor elimination constraints. Here it's important to mention that it doesn't take capacity into account, so it's not going to be exactly the same problem that we solved before. We relax for capacity, but so you won't. It's not exactly the same problem. We'd have to add also some other constraints for the capacity. But just for the sake of teaching you how callback works, I think it's this is sufficient. And so what we do here is that we actually, when we create the callback, we add some. We will start with the first part, which is checking the ID of the context. So checking if we are at the right event. So with the get ID. So what we say here is that if we're not at the candidate event, so remember the list of events that I talked about earlier. So if we're not at the candidate, so candidate is for when we have a new recognize it. So probably this one. Yeah. So when we have a new integer solution, so if we're not at this moment, then we just return. There is no point in doing anything. Now we will actually, so that it don't waste too much time. I will copy, I think, the part of the callback that I've already written here. So this is what we had before. So we want to get the arcs. So this is nothing. There's not much new here. Okay. So what we do here is that now just think that we are at some node in the branch and bound tree, and we have a new solution. So what we want is we want to be able to know what is this solution actually? What are the value of this solution? So what we do is that we call the get candidate point. So this is a function from the context. So the context here is some object, some CPLEX object that contains a lot of information. And when you're at the candidate level, at the candidate event, then you have access to this method here. And then we construct, as we saw before with the get value, we just construct the active arc. So we recover the solution. Now, here what we do, so here that's where I use network kicks. So we have to import it. So this is a library. If you don't know it, it's a library for graphs. I think I might not have installed it. So it's a library to construct graphs and solve graph algorithms in Python. So here I use it to find the connected components, because actually the idea is that we have we want to find subtours by looking at the different connected components of the graph. So if we have some multiple connected components that do not include the depot, then it means that we have some subtour. So then we will want to eliminate those subtours. So yeah, we have this here. And now, okay, so that's what it's doing here. We just find the subtours. And now we add the constraints. So this is the important part, or actually the other one about the get candidate point was also important. But this part is where we construct the new constraint. And here, what's I think the most maybe annoying part of this kind of callback with do CPLEX is that we cannot use directly the same syntax that we used before with do CPLEX. So this is one occurrence where we have to rely on the CPLEX API to add this kind of constraint. So here we have to use a different notation that is not as mathematics friendly, let's say, as the one of do CPLEX. So we don't just use Python operators. So what we do here is that so for each subtour we construct we add this constraint here. And so we have to use a different syntax to construct the constraints. So this is the left-hand side of the constraints. This is the sense. Oh, here and also I add more candidates, not just one candidate. So it's a list of constraints. So we go over all the subtours, and we have the right-hand side of the constraints. So it's a different notation, but it means essentially the same thing as the kind of constraint that we constructed with do CPLEX. And then we have this reject candidate here. So this is the essential part of the callback. There's also, yeah, I said you can store information, so I think we will have to add this as well. So we have, so for example, if you want to keep track of the number of cuts added, you can add some variable here, integer variable, to just where you add up the number of constraints added. But there's this one is more important. This is where we store the x variables of when we construct when we will initialize the subtour elimination callback. We will have to pass the variables of the model. So let's do it. So from VRP model, import build model, and from VRP data, import load instance. And again, so the model and the x variables. So build model. and we pass the instance. And now we will specify that MTZ is equal to false. So we won't add the MTZ constraint so that it makes sense to use this callback. And we're almost done. What remains to do? So if you remember here, the general the workflow of callback is to call the function set call, to create a callback, then to call the callbacks, the function set callback, which is a CPLEX function. So we have to get CPLEX. So that's also a function that is not directly from, that doesn't come from the do CPLEX API. So let's create like this callback. So we create an object as you would create any Python object. Then we use model get CPLEX to have access to get access to the function that set the callback, and let's call it like that, CPLEX, and then set that was the CB. I'm not sure why it doesn't recognize it, but and then so the CB is the name of it's the variable containing our callback, and then we call context dot ID and candidate. So we want the callback to be called at the candidate event, and I think we're ready to solve it. So MDL solve. Let's run the output. Oh yeah, we have to pass the variable. So it will be the variable x. Yeah, so x vars. So in our init function, we want to pass the x variable. So it's x here, and let's solve it. Context has no attribute ID. You see, this one works. So is it the? Oh, okay. No, it was not the right. Yeah, I didn't import the right context. I don't know what this context is, but it's from the CPLEX callbacks actually. So that's why there's another object called. Oh. Let's try again. Yeah. Okay. I'm not sure about. Maybe there's some typo here, but let's run the script that should work. So we get here a solution, and I think what's interesting to note is. Okay, so we have, so this is without the subtour elimination. So I ran it first. So if you look at the code here, the script, you'll see that we first run it without the callback. And then we see that there are some subtours in the solution. But when we run it with the callback, then you see that there are some, so this is from CPLEX. So CPLEX saw the callback, the lazy constraint callback. Then it used it, and we have there's a problem with the formatting. Let's run it again. Okay, and then we see how many cuts we added. So we see that we added 6 cuts, and in the end we have a solution that doesn't have any subtour, but still is not valid in terms of the load. As I said, it doesn't enforce the capacity. Those new constraints would have to add the other constraints. But that's essentially how callback works. So I think I'll stop here because it's already 4. So if you have questions, feel free to stay and ask me questions. Or if you have questions that are, yeah, I can answer them right now. Yeah.
It's curious because there
Yeah.
are different ways to solve MILP problem. Let's let's say branch on combination. So just wondering that when CPLEX, what type of method CPLEX each time use? Can we select the type that it's solved, or does the CPLEX tell us that which method it chooses to solve it?
Yeah, in the log it tells you which method it chooses to solve it. But if you solve a MILP, usually it will do some branch and bound. So usually it will solve. So maybe it won't use the simplex algorithm at the. I'm not sure exactly if you can probably have control over what you exactly how you solve the LP and things like that and how you branch. There are some callbacks that you can create.
It defaults,
but it's in default because yeah, I think there are there any other way that maybe that there are some other ways, but not that. It's usually the most common way, like branch and bound. I'm not even sure if CPLEX has another way to solve like a MILP that is not like trivial and could be like solved in the pre-solve or whatever, but without using the branch and bound. I don't know. I'm not like an expert in CPLEX, by the way, but I think it's usually it uses branch and bound. Yeah. Yeah. We're okay. So with the callback is that it's within the branch and bound. So whenever a callback is called, it's during the process. So it's not. If you didn't set the callback, if you didn't register it, of course it will have to solve it again. If you solve it twice. This is what happened here. I didn't show you exactly the script here, but the first time we solve it, or I'm not sure exactly where it is, but we solve it first without the callback, and then we solve it again after setting the callback, after registering the callback. So when we solve it again, we solve it again. So we solve it 2 times in this case, but
doing branch on bound. Reach the integer solution with the lazy.
Oh no, okay. So the solutions that are found that we reject, it's not when we're done with the whole branch and bound, it's during the branch and bound. And that's why callbacks are interesting, because it lets you control what happens during the process, during the branch and bound. So every time you're at the node, let's say somewhere in the branching tree, you have a new solution, then the callback is called. And then you decide what you do. If you don't want to add, and sometimes you may want to have just information about the new solutions, or you may want to store them yourself without using the solution pool. There's already a solution pool, but maybe you want to do some operations for whatever reason. You have control on that. So, but an example is those lazy constraints. So when you're at the candidate events, when you have a new incumbent, you have the control of what you want to do, and then you may decide, I will add a lazy constraint, and so I will reject all the solutions that are invalid, that are valid according to the basic model that I wrote at the beginning. So the one, for example, without the MTZ constraints, but it's not valid, and maybe you know that you will have subtors if you use this this model that is not complex enough. So you add yourself the constraints during the process. And the main reason usually is because in some problems, there are too many constraints. You have an exponential number of constraints. So you cannot just create them at the beginning, all of them, because it would be too many. So you want only to, or maybe it's not that it's too many, but it takes a long time. It makes a model too big. So you know that those constraints won't be violated that often. So you want to reject them only when they are violated. Does this make sense?
Yeah. So when we do a callback, so we want to reject that solution for any reason, and we want to add the constraint. So after adding constraint, we will continue from the branch node that we were in, right?
Yeah, so it doesn't, exactly. So when you add the constraint, it doesn't affect like not directly the way that you branch, because this is not a callback about like making decisions on the branching. You can have control over that as well with different callbacks, with different events and different functions. But here it's just you add some constraints, but the constraint will be valid afterwards. So it should be valid globally. Yeah.
So as you said, globally, so the subtool in this case is a global constraint which is valid, but
Yep.
is it added to other nodes or just the nodes that appear after the current node?
Yeah, okay. Later in the, so I think when it comes to lazy constraints, when you use the reject, so the lazy constraints here with the reject get candidate point and then this one, reject candidate. I think it's global all the time. I'm not sure. Maybe there's a parameter, but if you have a user cut, like we didn't have time to talk about that, here you can specify whether you want the cut to be local, which means only like in the subtree. Yeah, exactly. Or if you want it to be global. But I'm not sure about the lazy constraints. But usually I think usually when you have a lazy constraint, it's because it's part of the model. It's just that you didn't implement it so beforehand. So you generally want it to be global, I think. Maybe there are some cases where it's not what you want, but it would make sense for it to be global. But when it's a user cut, then it's just to cut the fractional solution. So maybe sometimes you want it just to be global, to be local and not global. So maybe that's why there's this parameter local here. Yes?
Well, without implementing callback, so CPLEX doesn't deduce by itself. If, for example, we have a symmetry problem, so it doesn't add this constraint by itself, or we need to figure that out and add it.
Oh, yeah. So if you have, there are some, maybe you're talking about some like cutting planes, like some standard cutting planes. Yeah, CPLEX usually it implements all of those cutting planes. And so I think I forgot to talk about that. But when you run a log, sometimes you see it says, I think when you add some callbacks, maybe it disables some cutting planes. But let's run this one here, for example. Maybe add, or this one with a problem, maybe 15, so that there's some chance that it adds some cutting planes. So let's have a look at the cut. Yeah, okay. Yeah, so this it generates a lot of solutions. I should have. I think it's 10. Oh, I don't have to look at all of them. But usually it provides information as well on some cuts that have been added. So you have, like here, for example. So those cuts are not, so this was in like the S3, so we didn't add any callback ourselves. So those were generated by CPLEX. So usually, I think there's a way to disable those cuts if you want like to add the cuts yourself, but by default, it adds like many of the standard cuts. But some of the one like the one that I wanted to talk about, like those capacity cut that we didn't have time to cover them. If you run the scripts that I wrote, you'll see that it adds additional cuts. So those were cuts that were not added by default by CPLEX, but it's not that many as well. It depends. Usually, CPLEX is very good to add like all of those symmetry cuts and all that. So, are there other questions? Yep.
And can it be able to solve non-linear problems? For example, with the relaxation.
Yeah. Oh, yeah. Thank you for that. Yeah, I just wanted before finishing, just saying that we didn't cover everything. So I focused a lot on like MILP and integer programming, but with CPLEX, you can also solve. You can add like piecewise linear functions. You can use quadratic programming. I didn't mention it here for some reason, but you have also some constraint programming. And there are some tools as well, like if you want to do some Benders decomposition. So CPLEX is a very big library, a very big software. So I think we've covered already. I didn't have time to cover everything that I wanted, so there's a lot of material that we could have covered otherwise. Yeah. I've not also myself. I use it mostly to solve like linear programs and integer like MILP. So I'm not very familiar with like quadratic programming or constraint programming. So I could not really answer questions about that. But I know it's possible to do that with CPLEX. So. Okay, so if you have anyways, if you have some questions, I'm gonna be here, so you can stay and I can answer your questions personally. So thank you for coming to this workshop, and yeah, have a good rest of the day.
I always use that GAMS for I just one of the solvers, let's say for MILP programming. I mean, if I solve this,
Yeah.
Yeah, and then I never use it. I mean, I have to try to see that how is the results would change or how which one is better. Probably GAMS is definitely better, but
GAMS, I don't really know. It's well-known software. Yeah, GAMS or how do you?
GAMS.
Yeah.
GAMS software, but again, when we go, usually there are lots of solver we should select. For MILP is one of them CPLEX that they have it inside.
Oh, okay. So GAMS is
general algebraic modeling software.
Okay, but it's the name of a company, or I'm not sure I understand.
Yeah. This is this is a software, but licensed software that being used by the economies. I mean, energy planning. I mean, just that's it.
Okay. I was not aware of
Yeah, just very common before actually become Python. Very popular. That's just.
Okay, it's kind of like some
programming
programming
it's very
language.
common because they have very advanced solver inside, especially for MILP programming and then programming.
It's like lingo.
But the problem is not that is not it needs a license.
Okay, but it's some kind of programming language. You said like it's been replaced by Python nowadays, so it's it lets you.
Still we can still choose.
Okay.
This is a Python.
CPLEX
is Python.
Yeah.
For this,
Okay.
you have to have the academic or something that somebody's paid for that. Otherwise, we cannot use it. I just wondering that if maybe you have a chance to use it, or just compare the.
But you're saying that with GAMS you can use CPLEX. Okay, so it's probably the same. You mean like comparing with Python, the Python version? Oh, I think it's probably the same thing because Python, it's not like CPLEX is not developed in Python. So what it does when you use the API, it calls some CPLEX software, like some which was developed probably in C, the C language. So I guess if you have exactly the same model with the same parameters and all, it should be mostly similar. Maybe in the callback there will be a difference because the callbacks are written in Python, and then if you use a faster language, it might be faster. But if you don't use any callback and it's just like the branch and bound, I'm pretty sure you will end up with something very similar. Yeah. But if you use another library like Gurobi is very it's mostly used, I think, nowadays more than CPLEX maybe. In some circles, so maybe Gurobi will be better in some problems. Maybe CPLEX will be better in some other problems. And this may make a difference if you change the solver. But just changing the language in general, I don't think it will make a big difference.
I had a problem with you see that the issues that I had, but actually it was solved because in Visual Studio. The version of the Python that shows for the virtual environment is still was 3.14. When I changed that to 12, we can write. We can run it inside.
Okay, perfect.
Yeah.
So how do you see CPLEX right now? Like as you said, Gurobi is getting more popular, and that's what I use.
Yeah. Yes.
So I just, for me personally, I feel Gurobi was much more easier, like in terms of like just general practice and writing stuff.
Okay, do
And
you?
even CPLEX installing the license
Yeah,
itself is
it's
missing.
easy, yeah.
So how do you see it? If you like, do you use it yeah, in your daily?
No, personally, I don't use CPLEX that much nowadays. I see that the thing is that the latest version is 22 point something, which means I think the latest like big revision was in 2022. So it's not being maintained since. Like there are some maintenance. I think one was maybe a year ago, the latest like maintenance version. So I don't know. I don't know if it's. I've heard that they're not really working in developing a new version. But Gurubi, I've heard that Gurubi is much more active than CPLEX. But, yeah, I don't know what it means if, like in 5 years, CPLEX will completely disappear, or if yeah, not sure. But I think it's similar if you know how to use CPLEX. Like you can create, for example, callbacks in Gurubi.
Yeah.
The syntax is a bit different, but it's more or less the same. It's the same principle. So if you know how to use one, I had not used like I've never used CPLEX in Python actually before preparing this workshop. I use it with other languages, but the syntax is a bit different. Like if there was no do CPLEX, for example, in C++, but it's more or less the same functionality. Like you have, if you use Gurubi, you would have the same kind of parameters. You would have the same kind of like want to change the emphasis or changing like the mid gap. The logs are also very similar. So and if you change the language, you use Java, C++. It's the APIs there are some differences, but it's more or less the same.
But using Python for callbacks and if you're going that deep into simplex, would it be making the solving slower?
It may, yeah. But it's always a trade-off. Like if you add, let's say you want to add some lazy constraints or user cuts, and okay, there will be some. The problem in using Python is that it has so the CPLEX solver will call the callback, and then there's some time to some delay between the time that it's like just for calling this callback in Python and executing it. But usually it's not that long. It's not going to be a 1 hour like to solve to call the callback, and maybe like a few maybe more than a few milliseconds, but it's going to be probably less than 1 second to do everything. So if you add some constraints that will improve the speed by, I don't know, 50%, and it takes hours to solve the problem, then it's still a win. But if you want really to optimize everything, probably it's better to use C or C++ to call your callbacks, to write your code. But in many cases, I don't think it would make a big difference.
Thank you for the
Oh, you're welcome.
Thank you.